Okay, so everything seems to be in place. So we are very happy to have Nikolay Bobev from up there. He's from Leuven, and he's starting the school. So he's teaching a course on supersymmetry, supersymmetric gauge theories, and superconformal theories in diverse dimensions. So we just need a few minutes to set everything up, and then we will start.
It's not going to work. It has to be here. Can you hear me? Yes?
Yes.
Okay. Yes, I think it works. Hi, everyone online. Should I start or should I start? Yes. Ah, okay. Yes. Thank you so much for having me over. Thanks to the organizers, Agnese, Alice, Davide, Nopado, and Carlo, right? 5 of you. Okay, thanks a lot. Yeah, so since we're waiting for 5 minutes, I just want to make this interactive. That's the reason you guys are here in this room, risking your life for science. So yeah, take advantage of that. And people online, well, I cannot really see the chat too much, but if you're really ultra shy, use the chat, but otherwise interrupt me by just speaking. I know it's antisocial. It's very social to speak, but you know, try that. Yeah, what else? I should put my name on the board maybe. So this is important. So I'm not gonna erase. Okay. So this is my name. You can call me by the first name. Well, you must call me by the first name. Here's my email for those of you who are really shy and want to or have a very detailed question that they cannot verbalize. So yeah, just send me an email. Online, I put some, I think these things are online that I sent you guys with the references, right, on the website of the school. Yeah, so you can find references that I've used on the website of the school. And what else? Well, yeah, I'll be using also other references as I go. I'll mention them. And anything else? Yeah, I was instructed that it's okay to not have a break and go for 1 hour and 45 minutes. You're strong people, you can do that. But if you have to go out, of course, yeah, I mean, we're all adults. We don't have to ask permission or something. Yeah, anything else? The organizers seem to be busy. Should I start or not yet, or? Yes, okay. I was given the green light to start. I also feel a little bit intimidated that all organizers are here, so I thought that this will not happen. All right, so what I'm going to talk about is superconformal quantum field theories in dimensions 2, 3, and 4. We'll mostly focus on 3 dimensions, just to fix a specific value of the dimension. And here will be to understand how these, so this means that you have 2 types of symmetry, SUSY and conformal symmetry. I will explain what this means. And these 2, you know, constraints on the kinematics of a quantum field theory lead to a strong constraints on the dynamics, and in some cases we can have exact non-perturbative results. So this is basically the slogan of the class. Understand the symmetries so that you can try to constrain observables like endpoint functions in a quantum field theory. And the focus will be on methods that do not involve perturbative approaches, so no Feynman diagrams and things like this. It will be fully non-perturbative stuff. There will be a price we have to pay. We have to look at very special observables, as we'll see later on in the class. Okay, so what's the plan? Everyone should have a plan, and I do. I will start with some intro to SUSY and conformal field theories. So since I'm the first one speaking in this school, I think it's a good idea to establish some language for these two topics. You will have actually courses that go into more details on the CFT side by Chris Herzog, and on the supersymmetric side, there will be a course by Gianguido Dell'Agata, who will go into the direction of supergravity. So I will give you a brief introduction, what these words mean. Then I'm going to go to study, well, explain a little bit elements of superconformal representation theory. Basically understand the consequences of imposing these two symmetries on the spectrum of operators. Then I will use what seems to be a very simple model or a class of models. But I think it's quite rich, and it will allow me to illustrate essentially many of the new tools that we have been understanding over the past couple of decades for dynamics of strongly interacting quantum field theories on these simple models, the Wess-Zumino model. I will explain what the model is, and then we'll go into studying the dynamics of the theory. So this will be basically 3/4 of the class. And in the last part, I will be talking about conformal anomalies and superconformal field theories in the dimensions 2 and 4. So I will mention some tools that we have to, again, compute exact observables here. So this is basically the plan. And based on this model, I will use this model as an example to also illustrate one new tool that we have developed recently that's called Supersymmetric Localization. So this is a certain tool that allows you to compute exactly the path integral of quantum field theory. So for those of you who are a little bit knowledgeable, you can say, well, I've read on Wikipedia that we don't know what the path integral is. That is certainly true, but nevertheless, we can exactly compute it, right? So that's the beauty of physics. We don't care what the mathematical definition is sometimes, often. All right, any questions about anything I said so far? Is the thing online working, Davide? Okay. Signed out. It says here, signed out. You have been signed out because you're currently signed in on another device. Just, okay, good. Let's proceed as if nothing happened, and oof, wow. Right. So, I will start off with somewhat lengthy motivation. And I think this is needed because you should know why we're doing things. Many of you may know what I'm going to say, so please interrupt me if it's too low. Yeah, generally, I've heard that the background of people is quite diverse, so please feel free to interrupt me and either slow me down or speed me up as I go. Okay, so why supersymmetry, you may ask. Okay, so first of all, what is SUSY? Well, supersymmetry is a symmetry that acts on the Hilbert space and relates bosons to fermions. That's roughly the basic definition. So without worrying about any indices and things like this and complications, schematically what you have is something called the supercharge, which is a generator of the supersymmetry transformation that acts on a fermionic state and gives you a bosonic state. I'm using the language of states and the bras and the cats associated with them because all of this can be made to work in ordinary quantum mechanics. So F is a fermionic state, B is a bosonic state. And then one essential property of this Q is that it anti-commutes. So I'm assuming you've seen the anti-commutator. And the commutator, I'll be using these things, of course, a lot, and I hope you're familiar. So H is the Hamiltonian, and Q is an operator. So essentially what we have is some kind of a strange operator that is like the square root of the Hamiltonian. It squares to the Hamiltonian. And this leads to very nice properties. Those who know complex analysis and complex manifolds will may associate this with the notion of a D bar and D and a ordinary differential D, but I'm not going to go there. So there's a close link between the physics of supersymmetry and the mathematics of complex manifolds. Okay, so what are the consequences? So one simple consequence is that energy is positive. So you imagine a state, which is an eigenstate of the Hamiltonian, with energy E. And I want to study what is the value, what are the allowed values of this energy. Ordinary quantum mechanics, in principle, E can be any real number. But here we'll have a constraint. So I have now, well, I'm going to normalize my state like this, and then I want to compute, this is very elementary stuff, I want to compute the expectation value of the Hamiltonian. Well, by definition, this is, I want to divide maybe by 2, so no, twice. I want to compute this because of this 2 here. Okay, so I'm computing twice the energy by computing this expectation value, but now I can use this algebraic relation to arrive at this. So now I can expand this anti-commutator and find something interesting. So you have the norm of this state plus the norm of the conjugate. So a dagger here is the Hermitian conjugate of Q. Norm square. Norms are obviously not negative numbers, and so I conclude that this is greater or equal to 0, and I follow the chain, and so I just proved to you that the energy is bounded below by 0. So that's one immediate consequence. Okay? So supersymmetric quantum mechanics is nice. It automatically leads to positive energy. And the same logic applies in quantum field theory. Another consequence is that if you have a state which is invariant under the generator of the supersymmetry Q, it immediately follows that the Hamiltonian on the state vanishes. This is immediate because Q squared is H. So supersymmetric invariant states have a zero energy. They're automatically a ground state. States are ground states. And this really is an important consequence and permeates everything that you're going to hear about supersymmetry and supergravity. Often, people in these two subjects, without even mentioning it, they are interested in studying the supersymmetric states first. So, for instance, in the context of a SUSY QFT, we will see that we're interested in studying some specific non-trivial states in the QFT that are invariant under a number of the supercharges Q. And those will be automatically the vacua of the theory. In the context of supergravity, we often want to study the bosonic solutions of the classical action that are invariant under a certain combination of the supercharges. And so again, we want to do that because those are, again, the zero energy configurations or the lowest energy configurations. Right. So this is important to keep in mind. Okay, so this is roughly what SUSY is and what it gives you automatically in 2 minutes for free. And then you may still ask, why is this interesting? I've already asked it here. Why? But I first answered what. So SUSY has applications. By this I really mean supersymmetric quantum field theory. Has applications in beyond the standard model physics. So these are attempts to extend the standard model of particle physics and explain some of the mysteries in it. For instance, the most famous application is that because of this kind of a relation, supersymmetry leads to certain cancellations in Feynman diagrams. So you have a loop with a boson that comes with a plus sign and a loop with a fermion in the loop that comes with a minus sign, and they cancel. And this leads to, let's call it like this, solves the hierarchy problem. This is an overstatement. I'm being recorded, so I will be chased down by the Peter Voigts of the world. But anyway. This is one of the main motivations to study supersymmetry in the context of particle physics. I should emphasize that we have not observed supersymmetric particles, as far as I know, in any kind of accelerator kind of experiment. So this is still kind of an unfulfilled promise, let's say. But whoever told you that supersymmetry is not a symmetry of nature lied to you massively, because physics is not particle physics and nature is not particle physics, which is a good thing, I think. So if you go down in some messy systems in the lab, like crystals and what atomic lattices, optical lattices, and so on, you can find supersymmetry appearing all over the place. SUSY appears in condensed matter, nuclear physics, and atomic physics. What you need to find are some Hamiltonians that are a little bit special and that have this kind of a property. And if you do that, so you have a system with equal number of bosons and fermions in it, what sometimes happens is that it kind of exhibits at low energy supersymmetry. So we will see an example of this as we move on. So this equals to 2 West Zumino model is one example an application of supersymmetry. Okay, and there's more highbrow motivations. So if you want to win $1 million, which of course you do, is you should go and solve the mass gap problem in quantum chromodynamics. So pure SUN Young-Mills, in 4 dimensions, we expect to have a mass gap, meaning that there's confinement. Well, if you prove that mathematically, you'll get $1 million, right? That's an official announced price, the Clay price. But we change the problem, right? In physics, we don't like to solve the problems we have in front of us. We change them to like a spherical cow type of situation. So instead of pure Young-Mills, if you start modifying the Lagrangian of the theory and add some fermions in it, you have what's called a supersymmetric Young-Mills. And then, in such types of theories, supersymmetric gauge theories, sometimes under favorable circumstances, we can exactly solve the problem. And we can see confinement in front of our eyes appearing. So these are exactly solvable in some sense. Again, every time I say exactly solvable, someone annoying is going to come and say, oh, but you don't know how to compute this. So in some sense, exactly solvable quantum field theories involving non-abelian gauge fields in which we can understand in detail the dynamics. I already mentioned that supersymmetry has long and productive interaction with mathematics. I've already mentioned this thing about complex manifolds. There's applications to topology. So for instance, there are examples of SUSY quantum field theories that compute for you topological invariants of 4 manifolds, which is an open problem in mathematics. Still, as far as I know, we don't have a classification of the topologies of 4 manifolds. And the claim, one of the many claims to fame of Witten is that he showed that the path integral of certain supersymmetric quantum field theory computes those invariants that are called the Donaldson-Witten invariants. This is just one application of many. And of course, something dear to my heart is that supersymmetry appears prominently in string theory. Okay? So, well, I will not have the time to talk about this, but there is, you will hear from the master himself a course on superstring theory, so you will have a chance to learn about that. The master is not me, it's Ashok-sen. Okay. Okay, so, good. Any questions?
I have a question.
Yes, I can hear you, but not very well.
It's okay now?
Yeah.
Yeah, a condensed matter system is generally a low energy system. So how SUSY appears in it? Can you please elaborate?
I didn't hear in detail the question except that you asked about condensed matter. But maybe type it in the chat or say it again.
Oh, sure.
Right, so I'm not sure what the question is, but I will go again to my point about condensed matter and try to clarify. What I mean here is that, so in the context of nuclear and atomic physics, these are discrete Hamiltonians, something like a lattice model, in which the Hamiltonian is very special and has this kind of property. In the context of condensed matter physics, it's well known that continuous quantum field theories arise in the infrared of a condensed matter system of some lattice model. The Kondo effect, the quantum Hall effect, and many, many others. The Ising model is an example, the critical Ising model. So in those situations at low energies, you have emergent symmetries. So for instance, you can start with a lattice Hamiltonian that doesn't have Lorentz invariance even. And then at low energies, you can find not only Lorentz invariance emerging, but also conformal invariance emerging. This is, for instance, the Ising model is an example of that. And so all I'm saying here is that if you allow yourself from a messy lattice many-body system to have an emergent conformal invariance, you may not be surprised that you also have superconformal invariance emerge. And that's what happens, yes. And this is a low-energy system, so how does it appear? Yeah, so I've answered it. Yes, good. So even I can expect your questions. That's good. Yes, so this goes by the name of emergent symmetries. And depending on your education, you may be more educated in this kind of a school of thought, that we should be reductionists and go and understand the mysteries of the universe by zooming in, studying quarks and strings and whatnot. But it's a perfectly good approach to stay at low energies and do experimental science and yeah, not worry about highbrow things. Yes. Okay. Good. So.
Hi, I have a question.
Yes.
So you said these supersymmetric invariant states are ground states.
Yes.
How would you classify them, as bosons or fermions or?
Right. They could be both. They could be bosonic or fermionic. Depends a lot on the case, yes.
Oh, I see. Thank you.
Yeah. So one quick way to motivate the study of superconformal symmetry, or either supersymmetry or conformal symmetry, is to look at a well-known result in quantum field theory that's called the Mandula theorem. So this is a paper that was written in 1967 by Coleman and Mandula, and it really pinpoints how hard it is to generalize quantum field theory. So most of the time, at some point you will start getting emails by crackpots with their favorite theories of the universe. And really, one quick way to kill all of those is to point to the Coleman-Mandula theorem. I'm not going to go over the details of the theorem, but I will make the statement as far as I understand it. So, Coleman and Mandula basically studied the question of what are the possible symmetries of the S matrix. So they're imagining some scattering experiment. So this was 1967. The logic of the day is that you can solve quantum field theory by studying analyticity properties of the S matrix. That was the slogan back then. And so now, 50 years after that, people are still going back to that slogan. But anyway, the claim is that the only possible conserved quantities, symmetries, that transform covariantly under the Lorentz group. So here, the context is already particle physics kind of context, meaning that you're starting from the Lorentz group, you know, as Minkowski and Lorentz and Einstein told us to do, and then trying to see what else can it be apart from the Lorentz group. In a theory, so it's a lot of words. I will start writing equations at some point. With non-trivial scattering, in dimensions more than 2 are the momentum p mu, the Lorentz generators m mu nu, the rotations and the boosts, plus scalar internal symmetries. So these are things like baryon numbers in particle physics and so on, flavor symmetries in general. And these guys, I will denote them by Zi, they commute with P mu, and they commute with M mu nu. That's what the word scalar means. Scalars under the Lorentz group. Okay? So that is the statement of the theorem. So it's a no-go theorem. You can't do better than that. Of course, if you have any intellectual curiosity, you'll immediately go against this and say, wow, how can I make this wrong, right? How can I do better than this? And so you really have to read the words here carefully. But before, I want to mention that the basic idea of the proof is to use the conservation of these currents, the momenta, and the Lorentz currents, transformations, and assume analyticity of the S matrix in the complex plane, and then as a function of the scattering angle of the Mandelstam variables. And the proof also assumes a locality. Okay. So the loopholes that we know. So of course this is wrong. There is more than that. But what's more is very constrained. That's the whole point of a no-go theorem. It's usually I'm not smart enough theorem. So you have to be smart enough to evade these things. So one obvious thing that you can do is to study free theories. And then they violate the theorem because they have trivial scattering. So here it says non-trivial scattering. So free theories, in addition to the Lorentz generators, they have infinitely many what's called higher spin currents. So higher spin means spin more than one. So you have a tower of spin 2, spin 3, spin 4, and so on. Higher spin currents. So there's the algebra is much, much bigger than the Lorentz algebra, but the theory is essentially trivial. You can compute any endpoint function by using the Wick theorem. Right. Okay. Another loophole is, well, obviously you can be in 1 + 1 dimensions because the theorem assumes more than 1 + 1. So if you're in 2 dimensions, many things happen. So someone jokingly said that the greatest discovery in particle physics is the greatest invention in particle physics is the discovery of the complex plane. So that's what happens in 2 dimensions. You have many special things, and you can see it in various ways. But one thing to immediately appreciate is that in one spatial dimension, you don't have a scattering angle. You only have a forward or a backward scattering. So the S matrix kind of trivializes. And so here you have many special things like integrable quantum field theories for which you can exactly find the S matrices. So this was studied by Zamolodchikov and his brother, who is also called Zamolodchikov. And if you have you also have the Virasoro algebra, which is responsible for many special things. Of course, you can violate a locality, non-local theories, so extended objects like p-branes. Those of you who know string theory have heard about beasts like that. And finally, of course, the 2 main players of our story is conformal symmetry. So what happens when you has extra generators in addition to the ones of the Lorentz group, and Poincare group in general, and these are the special conformal generators K mu, we'll see them very soon, and the dilatation operator D, which is a scalar. So there is an extension of the Poincare algebra to the conformal algebra. But the price you have to pay is that this symmetry actually requires that your theory does not have a scale in it. So this is applicable for theories of massless particles, roughly speaking. Okay, so you're avoiding the theorem because the theorem here assumed massive particles. You can't really define an S matrix for massless particles. So it evades the theorem, and the final one is supersymmetry. One assumption here is that they studied, Coleman and Mandula studied ordinary commutators. That was their algebraic structure. But if you allow for anti-commutators in the story, you can get what's called a graded Lie algebra instead of a Lie algebra. And then this means that there is fermionic generators of your symmetry algebra. So these P's, P mu and M mu nu can get extended by things like the supercharge Q I already mentioned. Okay, so these are the 5 interesting loopholes that I know of. And the last 2 will be the subject of this lecture. So if you're interested in interacting local theories in more than 2 dimensions, the only way to find them that are extensions of the usual Lorentz covariant quantum field theory is to look for these 2. Another comment is that string theory realizes all of the 5 loopholes in it. So of course you can have 3 theories in string theory. The string worldsheet is a 2-dimensional CFT, basically. Of course it has extended objects, D-branes and M-branes, and of course these 2 appear all over the place in string theory. Okay, so this is my motivational speech about why we should study superconformal field theories. It's bound to be interesting. Questions? No? Is this known, by the way? How many of you have heard about the Coleman-Mandula theorem before coming here? Okay, so not everyone. Good. All right, so now I will be much more specific, and I'll have many more equations. And I chose to focus on a specific example rather than giving you very general formalism. So we will study now the 3-dimensional n equals to 2 superconformal algebra. So the motivation is, of course, that there's interesting quantum field theories that realize this algebra. Otherwise, it will be an exercise in pure mathematics, which will be boring, of course. Okay, so for the next 2 hours or so, the 3n equals 4 superconformal algebra. This will sound like an annoying exercise in algebras, and I'll have many formulas, but we will use them afterwards to do physics. Okay, so mathematically, this algebra has a name, which to most of you will mean absolutely nothing. It's called OSP2/4. This is some compact notation for superconformal algebras. So the Bosonic algebra, meaning the usual things that have commutators, is SP4 times U1. So I'm using here complexified algebras, and I will use a reality condition that, by the way, SP4 is isomorphic to SO5 as an algebra. So we choose reality conditions on the generators such that we find what's called the, so that we have Euclidean conformal symmetry. So for the next, well, for most of the class, I will be in Euclidean space. So not in Minkowski space. I will work on R3 in this case. And this algebra is SO4, 1. Okay? So that's this SP4. Somehow I take a real slice which fixes that. Okay, so the Bosonic generators are the following set. I have the momenta. I have these special conformal transformations which you may or may not have seen. And I have, so these are, ooh, that doesn't work too well. These are momenta, special conformal. These are the usual SO3 rotations. This D is called the dilatation operator. It's a local rescalings of space and time. This R is called it's a U1R symmetry. That's why it's called R. From the point of view of the space-time, this is a global symmetry. Yes?
Excuse me, we cannot read these from home.
Okay, so I will not be using colors, but you heard what I said, so I'm not going to write things again. Momenta, special conformal, rotations, dilatations, and U1R symmetry. So this is an internal symmetry, meaning that it's a scalar from the point of view of space-time. Okay, no colors. It will be black and white. All right, and of course, the index I goes from 1 to 3 because I'm in three-dimensional space. Okay, so this is the minimal algebra of bosonic generators. Well, I haven't written the algebra yet, but this is the minimal number of bosonic generators. Of course, in addition to those, you can have what's called flavor symmetries, meaning some internal symmetries that act on your Hilbert space and are scalars in space and time. And we'll see examples of that. Good. So the fermionic generators are 8 fermions, for which I will establish a notation. So these are two-component fermions, and this is the set. So alpha goes from 1 to 2. So I have Q plus with 2 indices, Q minus with 2 indices, S plus with 2 indices, and S minus with 2 indices. So a total of 4 of these and 4 of these. Okay, these are called Poincare supercharges, and these are called superconformal charges, or generators, not yet charges. So, at this point I want to make a comment. I'm studying here directly the superconformal algebra. So the two loopholes that I just erased, the last two, I'm combining them and extending maximally the Lorentz algebra. You can study only supersymmetric algebras, and for that you have to remove these S's, and you have to remove the D and the K generator. So you can extend only the Poincare algebras with the Q's. And the application of those algebras is in theories with massive particles. Okay. Good. Before we go into the madness of really writing down this full algebra, which I'm going to do for you, I have to tell you the rules for Hermitian conjugation. So my goal here is that at least once in your life you've seen a superconformal algebra in full glory, so that you can sit down at home and check all the, details of this. So Jacobi identities and so on. So the Hermitian conjugations. So my Hermitian conjugation is going to look awfully like my plus. That's life. You have to live with this. When there is a bosonic generator, there's really no notion of a plus or a minus. Okay, so this is, I claim, a consistent choice. And then for the fermions, I have, so here it's important, plus minus alpha. Hermitian conjugate is S alpha minus plus. And finally, I want to emphasize how this generator acts, and also this one. These are scalars, and they will actually be used to label the states. And so if you have an operator or a state, O, the action of this D on it has a certain eigenvalue, which is called delta, and this thing is called conformal dimension. Okay, so this eigenvalue, I have an I here because of the minus here, so this anti-Hermitian operator, it's just a convention choice. So this minus introduces this I, so the eigenvalues are not real, but pure imaginary. Okay, and then R is a Hermitian operator, and so its eigenvalue will be called a little r, and it will be called an R symmetry charge. So it's just a U1, so I'm just labeling by the charge. Okay, so now we go into the mess of writing things out, and as I said, I'll be very explicit. I will first define some conventions about Pauli matrices. So I have 3 Pauli matrices, which you know from high school, or from Wikipedia, depending on where you got your education from. And I will also use some kind of antisymmetric tensor of SU2. So SU2 is SO3 locally as an algebra. So I have both an epsilon tensor for SO3, epsilon ijk, and an epsilon for SU2, which is this one. And so there will be various notions of sigma. So these guys are sigma with one index up and one index down. I should have written this, sorry. I will write it like this. So these are the sigmas with one index up and one index down. If you want to lower or raise this index, you have to use these epsilons. And here is how it works. The reason you have to introduce this, if you really want to do things carefully, is that these epsilons are the thing, these sigmas and epsilons are the things that act on the spinor index. So my spinors will be 2-component spinors, and that's why these are 2x2 matrices. Alpha gamma, epsilon gamma beta. So when you raise and lower one of these alpha beta indices, you have to be careful about the signs. That's really what you should remember from this story. Okay. All right, so this is kind of the starting point. And then maybe I'll keep these and erase this. So now I'm going to write down first the conformal algebra, and I'll write it in a way that is valid in any number of dimensions. The reason I said it at the beginning that I'm going to study 3-dimensional superconformal algebras is that in order to speak about spinors, I have to fix the dimension of space-time because the properties of spinors change as I change the dimension. But for the bosonic, for the conformal algebra, I can really formulate it in arbitrary dimensions. Okay, good. So I need more space to write down. So with generators somewhere there, well, somewhere, and here's their commutation relations. So you first have the kind of the most annoying commutator. I will also be committing another sin. I will be using I as an index and I as a square root of -1. I know. But you're all adults, so you should know how this works, right? Every equation that I write in this course will be morally correct, but maybe factually wrong. So this is the best type of equations. Okay, so this is really a parenthesis, not a commutator. Okay, so this is basically the rotation group in d dimensions. That's what I've written down. So this index, for me, strictly speaking, goes from 1 to 4, from 1 to 3. But here, the way I've written it applies in any dimension. Then the rotation generators, of course, act on the momenta. The momenta are vectors, and so they have to be rotated in some specific way. And of course, the special conformal transformations are also vectors, and they are rotated in exactly the same way. And another mortal sin is that K has an index K. Such things happen in life. Something that you may not have seen is that this the rotation operator gives a certain eigenvalue to the momenta. This means that the momenta have conformal dimension 1 according to my rule. And the special conformal generators have the opposite dimension. So this is dimension 1 and this is dimension -1. Finally, I have to tell you how P and K anti-commute. Commute. They give you this. And everything that I've not written down vanishes. Okay? So, more specifically, all of these generators that I've written down here commute with the U1R symmetry, with this big R. And also, Mij only gives you 0. That's kind of obvious. Everything that doesn't have an index cannot be rotated by the rotation matrix. Okay? Good. So this here is the conformal algebra in d dimensions. So this is SO d plus 1, 1. Okay? So we heard about Raul Gatto in the introductory speech. So he was one of the first physicists to appreciate the importance of the conformal group, the conformal algebra. So it's quite appropriate that we're mentioning it here in this room. All right. Now I should keep on going because I have superconformal in the title of my lectures, so I have to tell you what this is. So now you understand what the plus and the minus are. They're simply the charges, the R charges of these two generators. So this R is this internal symmetry, and it gives a charge 1 or -1 on the Q's and the S's. So this is the standard thing that you can read in many books and papers. Everything that's called an R-symmetry, what it means is that it does not commute with the generators of the superconformal algebra. As you see, I get a non-zero. And a flavor symmetry, roughly speaking, is such a symmetry that commutes with the Qs and the S's. And then, of course, something much more obvious is that these guys are fermions. So when you use, when you rotate space and time, they will have to rotate according to some rule. And the rule is basically you have to multiply by a matrix that somehow relates the three-dimensional representation of SO3 to the two-dimensional representation of SO3. So the adjoint to the fundamental. And that's this matrix, and epsilon ijk is the usual antisymmetric tensor in 3 dimensions. So you kind of see the reason now why I chose to do this in 3 dimensions, because, well, 3 is the first non-trivial one, bigger than 2, and also I don't have to speak too much about the complicated Lorentz structure in more than 3 dimensions, where I have, you know, a bigger Lorentz group. All right, so I'm still not done. I have to tell you how D acts on the Q, and it gives them eigenvalue 1/2. So the dimension of Q, the dimension of S is minus 1/2. When I say the dimension, I mean the conformal dimension. And finally, the momenta act on the S's to give you Q's. And the special conformal act on the Q's to give you S's. All right, so now I've told you how the bosonic generators commute among themselves, and I've told you how they act on the fermionic ones in gory detail, maybe in more detail that you wanted to see. But anyway, the final piece of information that you need is the anti-commutators of the fermionic generators. So you see here the structure of a graded Lie algebra. So far we've seen only commutators. 2 bosons you have to multiply with a commutator, a boson and a fermion again with a commutator, but 2 fermions you have to multiply them with an anti-commutator. I should get my minus and plus straight. So this is now anti-commutator. You get this, and then S's, as you can guess by now, anti-commute into the special conformal. And finally, and this is very, very crucial for constraining the dynamics of the theory, this identity that I'm writing right now is going to be very important later on. Okay. So some comments. So this here is a quantum field theory, if you wish, manifestation of the thing I started the lecture with, namely, this is the fact that 2 Q's anti-commute into the Hamiltonian. So if you choose this, P0 is, of course, P1 is the Hamiltonian. And so this is kind of in the same spirit, right? Yes? Oh, yeah. So, what's the complaint? I did something wrong. This one here? Yes. So it's a total mess. Yes. Good. K and Q, I should get an S, right? Yes. Thank you. Let me check. Yeah, this sounds about right. So now I've given you all non-vanishing commutators and anti-commutators, and my claim is that this is a consistent algebra. What does this mean? You can conjugate every operator in it with my Hermitian conjugation rules that I just erased, and you get a consistent answer because there's some i's here. So every I and every sign is chosen such that it works. And you can study the Jacobi identities or the graded Jacobi identities and see that all of them work out. Okay? So I have a consistent algebra. Questions? Yes? Yes. So by operators you mean yes, absolutely. That's why I'm being careful with the index on the S is up and on the Q is down. I'm trying to be careful here. At some point I will stop doing that, but yes. Sorry? D, yeah. D, I chose a convention in which D is not a Hermitian operator. It's completely a choice, yes. So I started with calling this algebra, the bosonic part, this one here, I call it SP4. By this I mean a complex algebra where everything is complex. But for physics, we want some real stuff. So you can either be in Lorentzian signature, so that will change a little bit some signs and some i's here, or you can be in Euclidean signature. So I'm choosing rules that are suitable for an Euclidean signature. Yes.
What about P?
Sorry, P? Yeah. What about it? It's a vector on R3.
Why not Hermitian?
P is not Hermitian. Where? P conjugates to S. Yes. This is important. This is important science, indeed. The conjugate of P is K. Very good. This ultimately is what leads to the notion of radial quantization in conformal field theory. Yes. I'm not sure what to say more at the moment, but
I'm a bit confused by that. If you do not extend the Lorentz to one plane, P is Hermitian.
yes.
So why is extension is Hermitian?
Yeah. Again, this will be a property of Euclidean conformal field theory. In Lorentzian, you have usually you slice your space-time with spatial surfaces and you evolve with the Hamiltonian. So P0 is a special thing. And then at every slice, you construct a Hilbert space of states and so on. And then on this, P is a Hermitian operator. And P0 has real eigenvalues. In Euclidean, I don't have a preferred notion of the time, so I can do various kinds of slicings. So this is a fact even without conformal symmetry. But when you have conformal symmetry, you can map the plane to the cylinder, to the ball, and to whatever, the upper half plane and so on. And these different conformal mappings give you different quantization schemes. I will have a comment on this later on, but this choice that I made is adapted to what's called radial quantization. So you order operators not, so when you compute a two-point function in ordinary quantum field theory, you do some kind of a time ordering, whatever. Advanced, retardant propagator, Feynman propagator, something like this. You have to specify how you order operators. Here, I will order them radially, outwards from the origin. And this is adapted to precisely that. So that's the long answer. Yes. Other questions? No.
Yeah.
Yes.
You maybe I didn't understand. So the anti-commutator of the Q's should be the Hamiltonian, right?
Right.
And in radially quantized CFT, isn't the dilatation the Hamiltonian?
Excellent. So by making an analogy, I confused you, indeed. So I started off with an equation that was like this. So now I should call this tilde because it's not the same Q. I started with this equation. And this is really a conjugate. So I have a Q and I have a conjugate of Q and I get the Hamiltonian on the right-hand side. So the better analog of this equation is actually this equation. Because the conjugate of Q is an S. And on the right-hand side, indeed, I see the dilatation operator. So indeed, as you say, in radial quantization, the analog of the Hamiltonian is the dilatation operator, and the analog of the notion of energies is the conformal dimensions delta. Yes. Good point.
Thank you. Thank you.
Yes. What I meant is that if you do Lorentzian supersymmetric algebras without conformal symmetry, this first identity will still be true. And then you will have a different notion of a Hamiltonian, P0, and then this will be more analogous to this. So I kind of mix the two notions of Hamiltonian. Good questions. Any other ones? All right. So I'm of course going slow. So my plan is slowly becoming unrealistic, but yeah. So it goes. For those who have read Kurt Vonnegut, they'll get jokes. For the other ones, read that book, right? Slaughterhouse-Five. No? No one's read Slaughterhouse-Five? Okay. It's a good book. Okay, so comment. Sometimes you want to realize a certain algebra. So I've given you an abstract algebra, and you may ask what realizes that algebra. A particular realization, which is very geometric and may give you intuition what goes on, is the following. So this is a geometric realization of the conformal algebra. Whatever, m dj minus. So the least intuitive is this guy k. Everything else should be familiar, hopefully. And of course, r is boring, is just a real number. So my claim is that if you use the definitions on the right here, on any smooth function on R3, you will get them to close this algebra. That's what it means to have a specific realization. Okay? And so these are the usual rotations, obviously antisymmetric. These are translations. These are local rescalings. This is just a multiplication with R. And this one is kind of harder to visualize. It involves surrounding a point sphere and doing an inversion around that sphere of radius 1 and then a translation. So it's somewhat confusing to think about geometrically. Okay, so this is how the conformal algebra is realized for function R3. Now you can be ambitious and say, wait, I have a superconformal algebra, so I should have some geometric entity. I should hope to have a geometric entity that realizes that algebra. Indeed, it exists. It's called superspace. So you extend the usual notion of a manifold with Grassmann-valued positions, coordinates. And then on that superspace, you have a geometric way to realize the Q and the S's. I will have a brief introduction to superspace later on. Keep that in mind. Yes. So everything I said was wrong. Indeed. So here now I've violated my own convention. Yes. Good. So I managed in 1 hour to make a bunch of mistakes already. Good. Right. So in principle, this is really on R3, not on R times S2. If I really want to be careful and compatible with what I said before, so this will close the algebra I gave you above on the nose, but this will not obey the Hermitian rules I told you about. So morally correct. Okay. Okay, good. Let's keep on going. So now algebra. It's the lesser known speech of Martin Luther King, who had a dream but also had an algebra maybe. So I have an algebra here, but I should be asking, what is the representation theory of this algebra? Well, I could be asking that. Why is this important? Well, Wigner and many other people have told us that quantum theories have a Hilbert space, and that Hilbert space realizes the algebra of symmetries of the quantum system. So if I'm a believer that I have quantum systems that realize this algebra, they will it in a certain way on their Hilbert space. So, and of course, I will not be mathematical here. You can really go and write books and read them about representation theory of supersymmetric algebras and superconformal algebras. But here I just want to give you a flavor. So I will be interested in finite dimensional unitary representations in conformal algebra. The notion of unitary essentially will mean non-negative norm. So not, well, this of course inspired by unitarity in quantum mechanics, but since I'll be in Euclidean signature, I should be more careful with my notions. So, representation theory of the superconformal algebra. So, finite dimensional unitary representations. Okay, so what we're going to do is we're going to label the representations by their commuting quantum numbers. You have algebras, you can find which are the commuting quantum numbers. Those are the dimensions, delta, the Lorentz spin, J, and the R char R. So every quantum state will be labeled by three numbers, three real numbers. J is quantized. So the notation is that the dimension of the spin J representation of spin J is 2J plus 1. So spin 1/2 is just a two state up and down spin. So that's a convention, and delta and R are not quantized, they're real numbers. Okay. So, as I said, operators are classified by their dimension delta. And so the basic idea of this representation theory is very much like representations of SU2 that you have seen in quantum mechanics. You start with some highest weight state, and then you act with the raising or lowering operators, depending on the convention, until you hit a state that vanishes. That's what I'm going to do for the next, well, I don't know how much time, but some time. Okay? So the details are slightly different. The basic idea is exactly that. So what are the highest states? I will start with the conformal algebra only, without supersymmetry. So O is a conformal primary. This is definition of the word conformal primary if it obeys this vanishing condition. It's annihilated, sorry. It's annihilated by the special conformal for all values of I. Okay? So this will be my anchor point. So I find such an operator in my quantum field theory, and then from it I can build a representation. So how do you build a representation? Well, you act with the momenta. Remember that K has conformal dimension -1 and P has a dimension +1 according to my algebra, and so the dimension of this operator OP is the dimension of O plus 1. So Pi and Ki act as raising and lowering operators. That's what happens. Okay? Good. So if you just have the conformal algebra, nothing else, you can construct representations of it using only the P. You find the space of conformal primary operators and their dimensions, and then act with the P to construct the full Hilbert space. If you have superconformal algebra, which we will have, superconformal primary is an operator O that, in addition to being a conformal primary, which is this, it obeys a different constraint. It's annihilated also by the S's. Okay? So now, if I want to study representation of the superconformal algebra, I have to find such operators O hat that obey both of these, and then construct the representation by acting. So build the representation by acting with P and Q. Okay? So these are now my raising operators, the P's and the Q's. These are obviously fermionic raising operators, and these are the bosonic ones. Okay. Okay, so this is basically the procedure. So now I want to make some comments and digressions on all this. So the first comment I already kind of made a number of times with this radial quantization. Chris Herzog will probably also talk about the conformal algebra in some detail, hopefully more than me, but really an important concept in Euclidean signature is radial quantization. And if Chris doesn't talk in more detail, I encourage you to read this review by David Simmons-Duffin, and in particular chapters 2 and 6. So that then it's really explained in gory detail this notion of radial quantization, and how you order operators radially. The punchline is that to every operator, O, every local operator O, you can assign uniquely a state in the Hilbert space in the origin of space, OI. Okay? And the notation is really suggestive. So to every state at the origin of space, well, I have a Hilbert space there with infinitely many states in general, and then to each of them I can assign a local operator, and I can move it to an arbitrary point x using the generators of the conformal algebra. This is called operator state correspondence. And in conformal field theory, it is really on rigorous mathematical footing. Well, as much as infinitely dimensional Hilbert spaces are on rigorous mathematical footing, which is another subject, but as rigorous as we can get in quantum field theory. And indeed, here, the Hamiltonian that acts on this state, in quotes, is the operator D, and the energies are the eigenvalues delta. So in conformal field theory, one of the first things that you should be asking is, what is the spectrum? That's what you hear a lot. By this, people mean the spectrum of conformal dimensions of all the states or all the operators in the conformal field theory. So this is analogous to finding the spectrum of energies in a quantum mechanical system. This is kind of the zeroth order question for you to understand the physics of the problem. Are you completely done if you have this spectrum? Of course not. Just like in quantum mechanics, if you have energies, this doesn't mean that you can compute everything. You just need the wave functions, the probabilities. But it's a good starting point. Okay. I'm not gonna talk more about this. Another thing that I'll be interested in, as I said already, is unitary representations, which means that there's some notion of a positive norm on the Hilbert space. And this leads to what's called unitarity bounds. And just to illustrate how it works on one example, consider, instead of being abstract here, I want to give you an example. Consider a state that is obtained by acting with this very specific generator. So I have an operator which is a superconformal primary. So this is a superconformal primary. So that's the highest weight state. And then I'm constructing what's called a descendant. These things that are constructed from the P's and the Q's are called descendants. Okay. Good. So I will study the norm of this state. Okay, and the assumption greater or equal. So now I would just plug in the definition. When I compute a bra, I have to Hermitian conjugate. Luckily, we have detailed rules for that. So this is just taking omega, Hermitian conjugating it. Sorry, this is O. And then the Q becomes an S. Now, I will use the superconformal algebra to rewrite this as the following anti-commutator. So I've written this as this plus the other ordering, but then I have to subtract this other ordering. Okay, but now, by assumption, this O was a superconformal primary operator. This means that S acting on that state is going to give me 0. So this vanishes since O is superconformal primary. It's annihilated by all of the S's. So far, so good, hopefully. Now, this anti-commutator, I emphasized at some point, I said, this is an important one. It's an S and a Q anti-commutator. It will give me bosonic generators on the right-hand side. I'll write them down explicitly here. IJK, sorry, yes. So I have to sum over IJK and then take this matrix. Now, what I didn't tell you, and I should have, is that this is a scalar. It doesn't have an index. Okay? So I'm studying the simplest possible example, a scalar operator, which is a superconformal primary. So when the rotation, something is wrong here. This is IJ. So M, the purpose of life of M is to rotate everything that has an index. But since O doesn't have an index, M just doesn't act on it, so this gives you 0. And these two will just give you the quantum number of O. The quantum number. So this will give you delta minus R, and then I will still have to carry this norm. Okay. So through this simple algebra, I have arrived, well, since I'm assuming positive norm, you arrive at an identity here that delta is greater or equal to R. Okay? So this is one of the consequences of the algebra that we have. We have a lower bound on the conformal dimension. Bigger or equal to R. In spirit, that's exactly the same operation which I used at the beginning of the lecture to prove to you that in supersymmetric quantum mechanics these are positive. It's exactly the same philosophy. So now you should notice that I've used here a very specific index 1 and a very specific plus. You should, of course, do this completely generally, and you'll find more bounds in the same spirit. So if you use another state, another descendant, which is Q1 minus on O, you find that delta is greater or equal to minus R. If you use yet another state, another descendant, which is just the momentum on O, you will find that delta is greater or equal to 0. Right? So all of these bounds are true, and you can combine them now to find that the strongest bound is delta is greater or equal to the modulus of R. So every scalar operator in a superconformal field theory in 3 dimensions with n equals to 2 supersymmetry should obey this bound. So this is amazing. You should appreciate. We just use pure thought to put a bound on the spectrum of the Hamiltonian. Okay? Pure thought here means only the kinematics. I haven't told you what is the quantum field theory. I haven't told you anything about it. I'm just assuming that there in the world of quantum field theory, there's at least one, and it must obey this. By the way, I just realized that I didn't explain what curly n equals to 2 means. Well, it means that I have 2 supercharges. I have 2 spinors Q, Q alpha plus and Q alpha minus. If you identify those and you have only 2 real Qs, you get 3D n equals 1. So you have Q alpha plus is Q alpha minus, and then there's no our symmetry. And so this is the minimal amount of supersymmetry a Lorentz covariant theory can have. I cannot have less than 2 because this alpha is the small, the 2-dimensional representation is the smallest representation of SU2, of SO3, spinor representation. Okay, so this is the minimal amount. So I'm doing n equals to 2, which is double that. Yes, I should. Any questions? Yes. So that's an important, yes. So that's why I started off with this positivity of energy and said that when the bound is actually saturated, these are important states. I'm coming to that, but let me finish off with some comments. So there's a completely analogous story. Essentially, everything speaking about here goes through verbatim. The only thing that you have to be a bit more careful about is that in 4-dimensional, the spinors in 4D, the Dirac spinor is actually reducible, so you can write it as 2 Weyl spinors, and that introduces some additional indices for the matrices sigma, but apart from this, everything goes through. And then you can check the details and find that then the bound is this. Okay? So this is why I can essentially treat at the same time the representation theory of 3D n equals to 2 superconformal algebras and 4D n equals 1. They have very, very, very similar structure. Okay. So now we go towards answering exactly the question I was asked. What if the bound is saturated? That's clearly something special. So take delta is equal to modulus of R. So I have 2 options. Delta is equal to R. So if R is equal to 0, delta is equal to 0, and the only such operator is the identity operator. Okay? Delta is something that informs you how the operator rescales as you rescale the distances in space and time, and the only thing that doesn't rescale is the constant. And so that's, I'm not going to talk about this. So delta equals to 0 equals to R is the identity operator, or the vacuum state, really the empty state. So according to the operator state correspondence, there is at least one conformal vacuum, and I call it that. Okay, so now I start with this sign. So I'm assuming R is positive, and then what you find is that Q alpha plus on O is equal to 0, and Q alpha minus on O is not 0. Okay, alternatively, you can have delta is minus R different from 0, greater than 0, and then you find exactly the opposite structure. So these operators O are certainly special. So instead of, if it was a generic operator, which is a superconformal primary, acting with the 4 Qs available to me will generate 4 descendant states, 4 non-zero descendant states. Here, I'm only generating 2 states because this one kills O. So these multiplets are called short multiplets. That's a terminology often used. And they're very special because they saturate a unitarity bounds. And this is the simplest example of a short multiplet, which is quite important. It's called chiral primary. And this one is called anti-chiral. The words chiral and anti-chiral are not very obvious right now, but there will be. I will mention briefly superspace, and then they will have a meaning. It's like holomorphic and anti-holomorphic, roughly. Okay. These are important operator and important states. The magical thing that happens is that if you know the charge under a global symmetry of this operator, you know the dimension. And if you know anything about quantum field theory, you know that computing anomalous dimensions is hard. Right? Beta functions, loops, blah, blah, blah. Computing charges is almost obvious often. You have a Lagrangian, you study every field in that Lagrangian and how it transforms under a certain symmetry. So basically this means that if you have such operators in your quantum field theory, you can exactly compute their anomalous dimensions, their conformal dimensions, in terms of their R charge. So that's kind of already an illustration what is so special about superconformal field theories. Okay. Something that I also want to make as a comment is if you didn't have any supersymmetry, you still have unitarity bounds, and this hopefully Chris will also talk about. Even if he doesn't talk about it, he will use it in his lectures on CFT. So I want to be very brief. Basically, you can, again, follow the same logic, study suitable descendants, use only the conformal algebra, and prove lower bounds. So non-SUSY CFTs, you get that delta is greater or equal to. Now, this I can do in any number of dimensions, because as I said, this is for scalars, and this is for, I'll call them spin S. By this, I mean that if you have SOD as a rotation group, you have symmetric traceless representations of S indices, and that's what I call spin S. Of course, I could have also other Lorentz representations, and then the formulas are a little bit more complicated, involving the Cartan of the Lorentz group and so on. Anyway, so such bounds exist for all unitary conformal field theories. They're not a property of supersymmetry, and they're very useful. The saturation of the bounds leads to either free fields or conserved currents. Okay. Yes? Well, this one is weaker than that other one. Okay? Because I can imagine R being more than 1/2, in which case, so this will always be true, even if I have supersymmetry, but this one up there could be stronger. If your R charge is more than 1/2, that one is actually stronger. Right? Because in 3 dimensions, delta has to be greater or equal to 1/2. That's, if you wish, the non-SUSY constraint, but the SUSY could be stronger than that, depending on the R charge. No, there's a gap. Yes. So such things will, yeah, good. So the bounds always smoothly go to each other. So sometimes spin 0 has to be studied separately. Also, spin 1/2 have to be studied separately. I will give you detailed examples of full multiplets, and you'll see how it works. Other questions? Okay. So the next thing I want to spend some time on. We have 12 minutes. So this will be a 12-minute lecture on conformal field theory. Amazingly, yes. So I want to spend small digression on conformal field theory and the constraints of the conformal symmetry without using supersymmetry, just so that you appreciate how constraining this whole game is. Digression on CFT. No SUSY for now. So you start with the conformal primary operators, conformal primaries with dimensions delta I. One quick thing that you can prove is that the one-point function for all of these guys vanishes. Whenever I write such a thing, I literally mean take the conformal vacuum and in it insert operators in your space-time. I'm not going to be writing the zero. So this is all one-point functions vanish. Okay, that was easy. Two-point functions. So I have two operators, OI and OJ, and I insert them at points 1 and 2. And you can prove, I'm not going to doing this, I'm not going to be proving this to you, but it's true that their two-point functions decay polynomially instead of exponentially. So if you have a usual quantum system or any kind of physical system, there's often the notion of a correlation length. And so usually two-point functions of operators go as e to the minus the distance between the points over something that's called a correlation length, psi. So this is the language of statistical mechanics, if you wish. In particle physics, if the particle propagating the force is massive, it will be the mass of the particle here. But there's always some kind of exponential decay, unless there's a special situation in which the particle is massless, or the correlation length is infinite, or very, very, very large, much bigger than the lattice spacing of the system, and then you'll have a critical system. So the Ising model, if you tune it to the special point, the critical point, this will be the form of the two-point functions, and then in statistical physics, these conformal dimensions are called critical exponents. So this is physics, okay? If you boil spaghetti at 274 kilopascals, this will happen. 272, some number in some units. The three-point functions, I will write them here. They're also severely constrained. And this is a long formula. But the important point to understand is that the two-point function is also completely fixed by the distance. So the two-point function is fixed by the distances between the points and the conformal dimensions, whereas the three-point function uses the distances and the conformal dimension, but also has independent information here. These Fijks are called structure constants or three-point function coefficients, various names, OPE coefficients also. We'll see why soon. The point is that this now is independent information because I have used the freedom to rescale the operators O by a constant to make the coefficient here 1. Once I have used that freedom, now the three-point function I can no longer rescale. And so these Fijk are useful, meaningful numbers. And so, in local conformal field theory, basically, local endpoint functions or endpoint functions of local operators in a CFT are fixed by, that is the claim, by the numbers delta, f, I, j, k, and then spins. So Lorentz representations. So here I've done 1, 2, and 3-point functions of scalar operators because I don't want to carry around indices. But the same constraints or very, very similar constraints on endpoint functions appear when you have a spin, Lorentz spin. And the really deep fact is that any endpoint function, not only the 1, 2, and 3-point functions, but of this data. Okay? At this point, because I haven't told you about 4-point functions and 5-point functions and so on. So this claim is true because of a deep concept introduced in the 60s and the 70s called the operator product expansion. This was understood most deeply, I think, by Polakov and Wilson at the time. So OP is operator product expansion. This is the idea in quantum field theory. You have a notion of an operator algebra. So if you really want to study quantum field theory abstractly, mathematically, this could be your starting point. I don't advise you to do it, but you know, you're free humans, you can try to do it. You get lost in math. But this is the basic idea. There is a notion of multiplying operators in a quantum field theory. So I take two operators, OI and OJ, scalars just to be simple, and I think of them approaching each other very, very closely. And then the claim is that as these points come together, I can think of these two operators as a sum, maybe an infinite sum. Generally, it will be an infinite sum here, of one operator inserted at that point. So this is a notion of an algebra. And the coefficients here, so these functions are fixed. They're known functions that are fixed by the conformal symmetry. I'm not writing them down, but they're known. These constants are dynamical data for the theory at hand. Okay? So now I have what this formal expression means is that I should use this inside of correlation functions only. So if I want to compute, for instance, a 4-point function, I can take the points close to each other and convert it to a sum of 2-point functions. So 2 by 2. So this is what this OP allows me to do. And when you have a non-conformal theory, this is a little bit of a murky subject. We don't know how this converges in general and so on. In a conformal field theory, things are very nice because I can use the conformal symmetry to isolate only 2 of the points in an endpoint function to be near each other and then use this OP. So in a CFT, this is a convergent operation. So repeated use of this OP allows you to even convert it to products of 2-point functions. If n is odd, I will have a 3-point function and a 2-point function. So knowing this, in principle, abstractly fixes all endpoint functions of local operators. In practice, doing that is a pain, but in principle, at least, it must be possible. So in the remaining 2 minutes, I will write down the 4-point function, and then I'll stop. for now. So the 4-point function is the first example where I can use the OP to reduce it to sums of some other objects. So what happens with 4 points is that I have 2 invariant functions of the conformal group or algebra. So I can take the distances, so I have 4 points, and I construct, so this x with 2 indices is the distance between xij is xi minus xj modulus, okay? So that's one. These are also called cross ratios because, well, they're cross ratios between the distances of the distances between the points, u and v. So u and v are invariant under the action of all of the generators of the conformal algebra. Since I've told you exactly how this is realized in terms of differential operators, you can actually confirm that by an explicit calculation, which I advise you to do. It's a character building. So if I take 4 identical scalar operators, this is the simplest case I can think of. So it's one operator O of dimension delta inserted at 4 different points, and I'm asking what is the 4-point function. The only possible answer allowed by conformal symmetry is some arbitrary function of u and v, because this is invariant. And then the covariance, meaning something that absorbs the dimensions of the operators, fixes this. Okay? So now I have an unknown function, and the claim is that the OPE, this rewriting there, allows me to write this function in the following way: sum over all conformal primary operators f o o o hat. So o hat, so o is the guy which appears in the correlator, o hat, let's say I. This is the sum over all conformal primaries. And then there's a function here, g, capital G, that depends on the dimension of O hat, I, and of course the spin, which I'll call L, of O hat I. And it's a function of U and V. The function capital G is fixed by conformal symmetry and can be computed exactly. So these are some known functions. So in 2 dimensions, these are in 2 and in 4, these are given in terms of hypergeometric functions. So they're explicitly known. And this should be squared. These f's now depend on your quantum field theory. So what changes for a given quantum field theory, a given CFT, is that this sum will run only over the primary operator. So the deltas are going to change, the spectrum is going to change, and these 3-point function coefficients are going to change. But the structure will be the same. So this is an illustration that if you know all the f's and all the deltas and all the spins, you can find the 4-point function, at least in principle. And this keeps on going for the 5-point functions and so on. Okay, so I'm going to stop here and we'll continue tomorrow morning. Thanks. You don't have to cut. Questions? Yes, yes. Yeah, sorry. So this G is a function that depends on the dimension and the spin of this operator. The operator over which I'm summing over. Well, I don't have a lot of time to spend on this, but I can point you to papers where this G is explicitly written down. It's not so hard to actually derive it in some cases, yes. Other questions? You can also ask me in the afternoon session, right? We have this Q&A. Also, people online, we have to hurry for the lunch arrangement here, but if you have questions, you can ask me in the afternoon. Thanks.